The pressure altimeter is a simple, reliable pressure gauge calibrated to indicate height. The pressure at a point depends on the weight of the column of air which extends vertically upwards from that point to the outer limit of the atmosphere. The higher an aircraft is flying, the shorter is the column of air above it, and consequently the lower is the atmospheric pressure at the aircraft. In other words, the greater the height, the lower the pressure, and by measuring the pressure, the altimeter measures height. Unfortunately, the relationship between pressure and height is not a linear one, so that calibration of the altimeter scale is not a simple matter. The situation is further complicated by high and low pressure weather systems, which produce pressure differences in the horizontal plane. Furthermore, the temperature of the air at the surface and the temperature lapse rate in the air above vary considerably, and this affects pressure. With all the variables and changing relationships that abound in the atmosphere, it becomes necessary to assume certain average or standard conditions. We can then base the altimeter calibration formulae on these, and then apply corrections appropriate to the deviations from standard conditions which occur with position and time. The conditions used for calibration are usually those assumed for the International Standard Atmosphere, or the EASA. Several assumptions are made in constructing the International Standard Atmosphere. The first is that at mean sea level the pressure is 1013.25 millibars. The temperature is plus 15 degrees Celsius, while the density is 1,225 grams per cubic meter. The second is that from mean sea level up to 11 kilometers or 36,090 feet, the temperature falls at 6.5 degrees Celsius per kilometer, or 1.98 degrees Celsius per 1,000 feet. The third assumption is that from 11 kilometers to 20 kilometers, or from 36,090 feet to 65,617 feet, the temperature is constant at minus 56.5 degrees Celsius. And finally, from 20 kilometers to 32 kilometers, or from 65,617 feet to 104,987 feet, the temperature rises at 1 degree Celsius per kilometer, or at 0.3 degrees Celsius per 1,000 feet. Having made these assumptions, the pressure corresponding to any given level in the EASA can be calculated from the calibration formula. Graphs or tables can be produced showing height in terms of pressure under standard conditions. These tables can be used for the manufacturer's calibration of the altimeter scale. Basically, the laboratory calibration consists of applying a series of pressures to the altimeter and checking that the instrument indicates the respective levels which correspond to these pressures in the EASA. Any discrepancies, if within certain agreed tolerances, would be listed over the operating height ranges as instrument errors. Static pressure is fed into the case of the instrument from the static source. As height increases, static pressure decreases, and the capsule expands under the control of a leaf spring. Conversely, as height decreases, static pressure increases, and the capsule contracts. A mechanical linkage magnifies the capsule expansion and converts it to a rotational movement of a single pointer over the height scale. The linkage incorporates a temperature compensating device to minimize errors caused by expansion and contraction of the linkage and changes in spring tension due to fluctuations in the temperature of the mechanism. This animation shows how the linkage works, but the actual arrangements are much more complex. The simple altimeter can have a setting knob which is geared to the pointer. With this knob, The pointer may be set to read 0 with the aircraft on the ground, so that when airborne, the altimeter indicates the approximate height above aerodrome elevation. Alternatively, the pointer can be set, before flight, to the aerodrome elevation, so that when airborne the instrument shows approximate height above mean sea level. Most aircraft are now equipped with a sensitive type of altimeter similar to the one shown here. The principle of operation is similar to that of the simple altimeter, but there are some refinements. For instance, a bank of 2 or 3 capsules gives the increased movement necessary to drive any counters and pointers. Also, jeweled bearings are fitted in the linkage, reducing friction, and thus the associated lag in indication. Finally, and probably most importantly, a variable data mechanism is built in. This, with the aid of a setting knob, enables the instrument to be set to indicate height above any desired pressure datum. The variable data mechanism can be used to set the desired pressure level, say 1005 millibars, on a pressure subscale on the face of the instrument. As the pilot turns the setting knob, the altimeter reading changes until, when the procedure is completed with the subscale showing the desired 1005, it indicates the aircraft's height above this pressure level. A change in altitude or surface pressure has no direct effect on the reading of the subscale. It only changes when the pilot turns the setting knob. British altimeters have a subscale setting range between 800 to 1050 millibars. The 3-pointer instruments shown here give a much more sensitive indication of height and change of height, but they do suffer from the severe disadvantage that they can be easily misread. It's not difficult for the pilot to make a reading error of 10,000 feet, particularly during a rapid descent under difficult conditions with a high workload. Accidents have occurred as a result of such misreading. Various modifications to the pointers and warning systems have been tried with the object of preventing errors, including a striped warning sector which appears as the aircraft descends through the 16,000-foot level. However, the greatest advance has been the introduction of the counter-pointer altimeter, shown here on the right. This gives a much more positive indication than either of the 3-pointer dials. Compare the simplicity of the indication.